All right, so welcome back. We're going to talk about this concept now of lift force. And so remember from before when we talked about net force of an object, when it's at rest with constant speed, it's going to be zero. So in this case, taking a look at our picture, if we had an object, let's say that an object was at constant speed, so we knew that the net force was zero. If the net force is zero on an object, what that's telling me is that whatever the net force is equal to, they must be the same number, just in opposite directions. And so, in this case, if I were to look vertically with this, we can see that this equals Fn plus Fg. Okay, so if I were looking in this plane, the only two objects here, if this object is in contact with the surface, is Fg and then Fn. And so if the net force is zero, really what we're starting to see here is that these two would have to be equal to each other, but opposite in direction. And so, if we have constant speed, then this is the assumption, is that they're equal to each other, they're just opposite in direction. So, in our other scenario, what happens if this problem is actually not a contact surface problem? What happens if the object's being lifted? Okay, so in this case, apparently, there are helicopters out there that can pick up entire houses, but in this case we have this lift happening. So notice underneath there's no contact between the object and the surface, right? So we have no normal force anymore. So what does this look like? So when an object's being lifted, the tension in the rope becomes the force. That's the vertical force being lifted. But it works both ways because of Newton's third law, and the rope is also exerting a force on the object, just in the opposite direction. And so really what we have here is not so much the contact surface part, it's saying that I have an upward force that would be my tension, which we're going to call lift in this case, and then this box also experiences this downward force of gravity pulling against it. So when I lift something up, pick up a book, lift a book bag, I have this upward force that has to overcome the gravity force in order for me to pick it up. And if these two things were equal to each other, then my net force would result being zero, indicating that the object's either not moving or it could be in constant speed. So the net force in this instance is going to be the lift force plus the force of gravity. So using the idea that F's equal to ma, each force can be broken down into two components. And so all we're saying here is that net force is equal to ma, where I have the net acceleration. The force of lift is still equal to ma, but in this case I have a lift acceleration. And then the force of gravity is equal to ma, but instead of a for acceleration, I know gravity is my acceleration in that instance. So really this lift force idea doesn't change the other components of what we've already talked about. It's just what happens when basically we have tension, when an object is being lifted up and it's not in contact with that surface anymore. So the lift force really tends to replace the normal force in this case. Okay, but we can break them apart. So let's take a look at an example and see what this looks like. A 1.8 kilogram ball is thrown into the air with an acceleration of 6.2 meters per second squared, and then it's asking what is the lift force exerted by the person throwing the ball. So we have this idea of net force. So we have F net is equal to F lift plus Fg. This wants us to solve for the lift force, so let's just rearrange for the lift force. So F lift is equal to, and then all I would have to do to rearrange for lift, because there's an addition, is subtract Fg over to the other side. So it's F net minus Fg. And so I have this idea now that I can solve for lift. Now let's start to break it apart. So the lift force, F net we know is mass multiplied by its net acceleration, minus the mass multiplied by gravity. Now, the mass units are the same here, and if you can kind of see it and are comfortable with it, you can actually factor out the mass here and then see right away that it really is just acceleration minus gravity. So the net acceleration minus what gravity would be. But for our cases here, we can just leave them included and not factor, but just know that if you do factor it out, you will get the same answer. So we know that this thing is 1.8 kilograms for the ball. And the acceleration from a net standpoint, it's thrown in the air with an acceleration of 6.2 meters per second squared. That's the net acceleration that this thing is experiencing, 6.2 meters per second squared. Multiplied by, and then I have 1.8 kilograms, and my gravity is pulling downward. There's my negative 9.8 meters per second squared. That tells me that my lift force is equal to, and my net acceleration overall was applying 11.16 newtons. Now notice here I've got a negative gravity and it's being subtracted. That's going to change this to an addition, and it's saying that I have 17.64 newtons of force coming from my force of gravity. So that means that my lift force works out to be 28.80 newtons heading up. Right, I get a positive value out of this. Correcting for significant digits in going through, I have 2 in each of these, so I know I'm going to have 2 here. I've got 2 going here. Gravity's a constant, so it doesn't count, which means I have 2 there. When I add these together, they're both in the ones place, which is going to go to my ones place for my final answer. So that's going to make this into 29 newtons going up. So really, what is this question getting at? It's saying that in order for me to overcome gravity and achieve this 6.2 meters per second squared of acceleration, I actually have to throw the ball upward with 29 newtons of force. Now the second that I let it go, gravity is going to pull it back down with 17.64 newtons of force. That means that if I'm throwing up a ball with 29 newtons of force, gravity pulls it back down at 17, the net movement of the ball upward is coming in right around 11.16 newtons of force, actually moving it up. That's the net force moving upward. So it actually makes sense that my lift force is a larger number here because gravity is slowing it down, but the ball's still moving against gravity going upward, which means that the overall force must be strong enough to overcome the gravitational force. So it does make sense to get this bigger value. So let's take a look at another scenario. A person in an elevator is going down with an acceleration of 2 meters per second squared, and if the combined mass of the person and the elevator is 3,500 kilograms, then what is this lift force? And so again, it's asking for me to rearrange for the lift force. So F net is equal to F lift plus Fg. There's my first part. Then I can rearrange the same way I did from the last one. Now, after that, I can start to expand my terms out. So I can say F lift is equal to the net acceleration minus the mass times the gravity. It's the same thing I did from the last problem. And then I can start to plug in my values. So person in an elevator going down with an acceleration of 2 meters per second squared. So here, I'll use a different color. Here's my net acceleration. Right, it's going down at 2 meters per second squared. Now, going down also indicates that this thing should be a negative. And so, as I move down through here, through my answer, I can see in my next part that I have 3,500 kilograms. Notice the negative that pops up with the 2 meters per second squared. And then I still have negative 9.8 and that minus. So I can tell that when they multiply together, I'm going to end up adding them. So note the negative acceleration that's there. At the end of this now, notice that my net force is actually moving downward. That makes sense because it says in the problem that the elevator is going down. So the net acceleration or net force is indicating a downward motion. My force of gravity 34,300, and that means now that my lift force is 27,300 newtons heading up, and then when I correct for significant digits, it's 2.7 times 10 to the 4 newtons going up. So same thing as before, but notice now this time that my lift force isn't as strong as my force of gravity, right? My force of gravity is 34,300 newtons, but I'm only lifting with 27,300 newtons, or 2.7 times 10 to the 4, so that means that the net force is actually going down. If you think about an elevator, when you get into an elevator and you go up or down in an elevator, if you were moving downward in an elevator and there is no opposing force pulling upward on it, that would mean that you would just be in free fall. And that would be a very scary situation if you got on a third floor elevator and you want to go down to the ground floor and there were no resistance in the cables causing you to move down at, a comfortable speed. And so there always is a lift force in there in the cables, in a tension sense, that's causing you not to go into free fall. Similarly, if you're moving up, that means there has to be a greater tension in that elevator cable because you have to overcome gravity to go upward in the elevator. And so objects that travel upward, my lift force should be greater than my gravitational force. And objects that travel downward, the lift force should be smaller than my gravitational force. And that's more just to give people kind of comfort as they're moving down, so they know that this object, for instance, wouldn't just be in free fall with a group of people stuck inside of an elevator. So that kind of sums up Newton's 3 laws. We spent quite a bit of time going through and kind of examining different problems. And so you're ready for the next set, and then you're ready to kind of start up a little bit of getting ready for the quiz, getting ready for the test, that kind of stuff. So let me know if you have any questions.